exponentially. We choose our k and alphas to make our average system exponentially go towards the origin. So just like before, we know we can only possibly leave this compact set, which will really just end up being the sphere, through the inner boundary. We know our systems will converge just towards the inner boundary, and we don't have to worry about them flying out the other way. Okay, and then doing that, this is just pretty much a restatement of the original theorem. It's saying that if your average system converges towards the origin, then so does your actual system. And the way you do it is you pick these annuli, and you have these r's, these small r's, and these big r's, which is the actual annulus, and you pick a delta as small as you want, and you say, okay, well, whenever we're inside this annulus and our distance from the boundary is bigger than some delta, we can talk about these systems, and you can shrink this annulus as small as you want. And your average system goes directly towards the center, towards the origin. And just sort of by the triangle inequality, you could show that your actual system, sorry, I should mention, I also, for a system like this, I point out that we assume our average system satisfies a property that it's always going to be at least delta away from this boundary. So our average system can't do something like go along this boundary and then go towards the origin, because our actual system maybe would be wobbling around outside of the boundary. So we have these conditions that it stays inside the interior. The average system goes towards the origin, and by shrinking this annulus and doing this analysis over and over again, you can show the actual system goes towards the origin. And so I'll just show the comparison of the
actual system goes to the origin within delta or something.
Yeah, it goes in. You pick any delta you want, and you can pick small enough epsilon that it'll go within the delta of the origin for small enough epsilon. Yeah, it won't actually. We can't ever guarantee it'll go to the origin because it's not.
I assume that. I mean, from a practical point of view, sort of the coefficients that become unmanageable with delta too small.
Well, just the epsilon. Actually,
because your derivative is blowing up, so I assume that thing.
The derivative is blowing up, but the average system actually. The average system. So in this case, all of these, it is actually smooth everywhere, and that's sort of an assumption we make also, that the actual average system is differentiable actually at the origin, even though the original one isn't. And although we can't really define it there because the original system, we can't really take its derivatives at the origin, when you go through the analysis, that actual delta you pick becomes independent of your k and alpha terms. You can pick some k and alpha that your system will always go towards the origin. And the inner delta, you can make it as small as you want, just in terms of epsilon, which is this frequency here. And because practically, if you look at the actual controller, it's nice.
Doesn't a lower bound on the derivative in that compact set of the, say, the square root of x term enter into the constant somewhere?
Yeah, it does.
Okay.
So yeah, it would.
I mean, something must be.
Yeah. So
giving it.
Well, I mean,
yeah, you're right.
In your numerics, it's like something does go wrong. Right? So
Well, but I'm also guessing that from a practical point of view, in the controller, some coefficient must be getting weak.
yeah, you're right. That's I should have said this omega does get. It has to get infinitely big if you want to get infinitely close to the actual origin. I was just saying these k alphas don't, but you're absolutely right.
But that's also the case with the baseline design. So there's something different here. Epsilon has a more challenging task here than in the baseline design where everything is smooth.
It does have a more difficult task, but in practical application, it doesn't have much difference because of the.
It makes you wonder if there's a better theorem than if there's.
Okay.
That's, I mean.
No, I don't think that there is a better statement. But something in the proof, you're asking the right question. Really, where is the condition on
this case with the square root, it's this inner boundary. The smaller radius r gives you upper bound on the derivative of square root of x. And you're right, as this r gets smaller, that upper bound on the derivative of x outside goes and it diverges. And so as you make this delta that you want to converge to smaller, to satisfy that condition, your epsilon, or your omega, your oscillating frequency also has to keep getting bigger and bigger. And yeah, you can't actually ever force it to go all the way to 0 without having an infinite omega. So,
Another question is, you know, you chose at 0.5, right? But you could have
Yeah.
chosen anything different from 0, I guess, right?
well, according to this, you could choose anything different from 1, but really you don't want to choose anything outside of, you don't want to choose something bigger than 1 because,
Yeah, something between 0 and 1, I guess.
yeah, between 0 and 1 is a good choice. Because you don't want to be dividing by,
So the analysis would be the same, I guess, right? You could state that here for, you know, any R, between, you know, 0
Yeah.
and 1, right?
yeah,
He does.
yeah, that's how I state.
Oh, sorry, I didn't see. It was too fast.
Yeah, sorry, that was just thing, I just wanted to motivate why we
Okay.
didn't want to use these not differential control. And,
So maybe
well, here it's just, it's not even showing that specific form. It was just, this theorem is talking about this Lie bracket averaging outside of these complexes. And, that was part of the proof. And then this was just an example to demonstrate in these two dimensions, you're never going to actually go to 0 and stop, but you still see some benefit in this new controller because the controller's, its size actually does get smaller as you approach the origin. And so this is, again, you have sort of a hill, you're being pushed away, and you just want to go to the origin. And I'm just going to compare the two controllers, the original one and the r equals 1/2 choice. And I put an X in line, so it's one of those two. But here's the two trajectories. I don't know if you can see that one really well, but you can see that initially they look pretty similar. The blue is this r equals 1/2 choice, and the dotted black, which you could barely see, is the original controller. And in the beginning, actually, this new controller is worse because you have, if you look at the actual control, you have a 2K term, which in the beginning, when the size of X is large, you have this bigger control effort. You can see that here too. But eventually, you can't see it here. I'll zoom in on the next slide. The control effort does get much smaller because what ends up happening is when the size of your vector gets small, the overall control effort gets small too, and the whole system sort of stabilizes to a smaller ultimate bound. And so here's just zoomed in, and this is just the last half second of the simulation, and this is sort of the ultimate bound that the system reaches with the original controller and with the new controller.